Okay guys, let's take a look at today's lesson. What we're going to look at is Lagrange error bound. So we've learned about two other types of errors that I'm going to review in just a minute. These two right here. We've worked with those before. What today's type of error bound is basically picks up all the rest. Anything that's not an alternating series, or anything that you haven't used the integral test for convergence to prove that it converges, it picks up everything else. So this is quite a large, big concept. The first thing that I would like to do is kind of go through vocabulary, all the vocabulary of what it is we're actually dealing with. Once we build that, then we'll get into the specifics. So, like we've discussed before, a function can be represented by a power series. We have written them before. The function can equal the power series. A partial sum would be the sum of the first few terms, however many that you are asked to do. That's called the partial sum. The first few terms of the series. Okay? I'm sure you're familiar with this word already, partial sum. We've been doing that for a while. This may be a new concept to you. That's a vocabulary word. They call the tail is the rest of the terms of the series after the partial sum. So kind of like the leftover, the part that you're not using to estimate something. We know that we can use a power series to estimate a function. And if we go to infinity, it is the function. So the tail is the rest of the terms. And this is just a clarification. Sometimes it just needs to be said out loud what it is. The remainder is the number. It's a quantity that you get by adding all the terms in the tail. I mean, that's what it is. It's all of the leftover terms. Whatever the value of those are, it's called the remainder. We've talked about the remainder before. Remainder is a math word for the error. So let's look at this next scenario. We have our function. It's equal to the partial sum, which we just defined what that meant, plus the remainder, which is the tail, the value of the tail, or the error. So the error is the error you make by assuming that the function is equal to the partial sum. Okay, that's the error is the error that you make by assuming that the function is equal to the partial sum. So the error is the same number as the remainder. Now it's kind of obvious, but it needs to be said. The error is the same number as the remainder. So an error bound is a number known to be greater than the absolute value of the remainder or error. It's our bound. So when we were looking at alternating series, those that converge, those that met the three convergence hypotheses, remember, alternating terms decreasing in magnitude, limit is 0, that absolute value of the first term of the tail was the error bound. Remember that? We would take the next term, and that would be the bound on the error. So that's what we did with alternating series. And if you have an alternating series, you can use this type of error. You don't have to use Lagrange error bound. So with alternating series, we can handle them like we have already handled them with that kind of error, alternating series error. This one we used in the last unit, the integral test for convergence. And we used, if we use this test to prove convergence, then there was, if you'll remember, there was an error part attached to it. We did a little bit of work on it. I'm going to go ahead and copy that error part down here just so that's a reminder from the last unit. Whether maybe we all remember it, I don't know, but I'm going to go ahead and write it down. So this would be a reminder for our integral test. So if you were proving convergence with the integral test, and you could use this type of error, the error that you would get, the remainder r sub n, is equal to the true sum minus the approximate sum. It's bounded by this integral, and we worked with that in the last unit. So for a very few, not a whole lot, we're talking, we don't use this test we don't use this test a lot, so this error we haven't practiced a whole lot, but that is an option for you. Okay, it's an option. So now we've talked about the types of error we've been looking and working with. Now we're going to talk about Lagrange. So Lagrange covers everything else. And what he did, it's named after him. It's called the Lagrange remainder, or the error. What he showed is that the error is exactly equal to the first term of the tail, but with its derivative evaluated not at the center, x equals c, not at the center, that's, we expand the series around the center, but at some number z, which is between c and the value of x at which we are evaluating the function. Okay, let me translate that. So, z is a number between c. Okay, c is where we have our series centered, and say we have it centered at 5, and say we want to use the series to approximate the function value at 5.5. So z would be a number between 5 and 5.5 where, okay, let's say where we can find an upper bound for the derivative. So like where the maximum derivative value would be. So I'm going to say that again, because z is usually what drives students crazy. Because z, who knows what z is, right? I mean, it's going to be different. So again, z is a number between the center of the series and where you're estimating, like my example was, but if we are centered at 5 and we're using the Taylor series to estimate 5.5, z is a number between 5 and 5.5 at which the maximum derivative value will occur. Okay, and I'll have to say that again, I'm sure. You should, so write that down. If that's making absolutely no sense to you, which maybe there's somebody in here that has no idea what I'm saying, write it down. Okay, so z is a number between c, the center of the series, and the value of x that we're estimating. It is the location where the next derivative has a maximum. Okay, now we're going to talk more about z when we get to this formula. So I'm just introducing it to you. So what he came up with was a formula to find the error bound. It's not the actual error, it's a bound. So this theorem right here, if a function f is differentiable through order n plus 1, remember n plus 1 is just a fancy way to say the next term. So it's differentiable through the next term in an interval containing c. I think we all hopefully by now know what c is. Then for each x in the interval, there exists a number z between x and c such that this is going to be true. Now this first part should be quite familiar with. That's the Taylor series part. This is our remainder, and we have a formula for our remainder. This is the formula that Lagrange came up with. Now this formula should not be like outside, just a crazy looking formula. If you will compare it to our normal Taylor series formula, the nth term, this one right here, general term of the Taylor series formula, you'll notice that, see the denominator, it's n plus 1 factorial. See, it's regular n factorial, right? It's the next denominator, the next term. This right here, the x minus c to the n plus 1, is the next one from this, x minus c to the n plus 1. The only kind of unusual part is instead of naming a derivative at the center, what he did was he named the next derivative not at the center but at some unknown value z. So you can probably guess that that is the number that drives people crazy. Okay? So it is the maximum value of the next derivative between x and c. That's what it stands for. That's what it stands for. Kind of get that in your head. It is the maximum of the next derivative. The maximum value of the next derivative. The one after where you stopped and chopped that off. Okay? Now, if we're lucky, which we are going to be on the very first problem that we work together, it's handed to us on a silver platter. They give us that. If we're not as lucky, we're going to have to investigate it and figure it out. And that's like the second problem we're going to do. Okay? So let's take a look at our two examples that we're going to be working. Okay, for our first one, we're kind of handed everything. We don't even have to, we do have to find the third degree Taylor polynomial, but we don't have to find derivatives and derivative values in order to do so. They already give us the derivative values. We've worked some like this before. So this would be like an AP problem. It starts you out just finding a Taylor polynomial. We all should be able to do that without a problem. We've been doing that for several days now. So let's find the third degree Taylor polynomial for f. We're centering it about x equals 2. So notice that my function value at 2 is 6, so that's how I start out my polynomial. We can say p of x or p3 of x. We'll just say p of x. So we start out with the constant 6. We're using the Taylor's theorem, using the formula to derive this. Our first derivative value at 2 is 4, so we would say plus 4. And then we're centered at 2, so times x minus 2, and we could, that would be to the first power over 1 factorial, but we don't typically put that. Our second derivative value at 2 is negative 7. So we have minus 7 times x minus 2 squared over 2 factorial. And our third derivative value at 2 is 8. So plus 8 times x minus 2 cubed over 3 factorial. No need to simplify. That will be fine leaving it like that. You don't have to simplify. So that will give us our Taylor polynomial. What they have asked us to do is to use it to approximate f of 2.3. Alright, so this, of course, we remember stands for x. And everywhere in the polynomial that we have an x, we're going to substitute it with a 2.3. We would have our calculator, and we would put that in our calculator, and we would get this. Now, why is that a function approximation? Do I even know what the function is? No, I don't even know what it is. It's an approximation because I'm using the polynomial to find it. You could have easily had said p of 2.3 equals 6.921. So either one of those would be fine. Alright, see, we're good, right? Easing into it. It's going to be okay. Alright, b. The fourth derivative, now let's take note here. We've got to be paying attention. Where did we stop this polynomial? What derivative? The third derivative. So according to Lagrange, it's the next term that's going to bind our error, kind of like the alternating series, just with a little twist. So it's the next one. It's the next derivative. It's the fourth derivative that's going to provide us the maximum value to put in our formula. Now, with that in your head, we're going to read part B. It says the fourth derivative of f satisfies the inequality. The fourth derivative of f is less or equal to 9. Why in the world would they tell us that? Exactly. They are handing it to us on a platter. You just have to be able to know what they're handing you. They're giving you the maximum derivative value of the one that we're interested in, the fourth derivative. That is the maximum derivative value on that interval. So that's what we're going to put in for our mystery f of n plus 1 of z. That's what's going to go there, the 9. Okay? For all x in the closed interval. Why are they pointing this out? What does that stand for? That's our c value, right? And what does that stand for? That's our x value. Remember, z exists between c and x. Our mystery maximum value exists between here, and they've handed it to us. If they don't hand it to us, like they're not in here, we'll have to figure it out. But they tell it to us right here. All right. Use the information to find a bound for the error. Bound for the error is a code word for Lagrange error bound in the approximation of f of 2.3. All right, so I'm going to write the formula, and it'd be good for you. The more you write it, hopefully the more it'll just kind of stick. So let's just write the formula, the blank formula, and then let's fill it in. Let's sub into it. Okay, so we're looking at the next term, the fourth derivative, to the fourth power over 4 factorial. So let's fill that part in. Again, we are binding, our error is bound by the next term, the one that right after this one. Now I'm writing it without the maximum derivative value there, just so we can talk about it just a little bit more. This c, we were already told, we already know what c is. We already know this is a 4 and that's a 4 because that is the next term that we would have written or would have gotten to. This is what is sometimes difficult to find, but in this particular problem they handed it to us. It's a 9. So, and look what they told us, that this is less than or equal to 9. So that's the same notation that I'm going to use right here. Less than or equal to, and then that's rewrite that with the 9 in there. So 9 times x minus 2 to the 4th over 4 factorial. To actually find the error, so that is our vehicle to be able to find the error. What do we need to do? What would we put in for x to be able to find the actual error? We put in the 2.3, and we'd use our calculator, and we would figure out what that is. And that error is actually comes out to be .003 with other decimal places, and this is called our bound for our error, for the error bound. Okay. Now, when I put equal here, I'm saying that this is equal to that. These two are equal. I'm not saying anything about this. This is less than. So this is the bound. Our error, the approximation that we got up here, is accurate within this bound. So the next part of the question asks us to find an interval for our answer, such that our, the for real function value is going to lie between A and B. Well, how would we find that? The for real function value is going to lie between two numbers. How are we going to do that? Exactly. We're going to take our estimate and we're going to add and subtract the error that we found. That's how we're going to get our interval, just like we got our interval with the error bound for our alternating series. Same kind of technique. So let's calculate that. And why am I using or equal to on that? Because that's what they used. Because that's what they used when they told us the maximum derivative value. That's why. That's our bound. And also, I mean, they didn't even leave it to chance. They put it right here, too. Okay. So let's answer part D. Could our real function value equal 6.922? Yes. Why? Because it lies in the interval, right? It's in the interval. Okay. What about 6.927? Could our function value be 6.927? No. And why? Exactly, because 6.927 does not lie in the interval. What a powerful tool to have. I mean, in the upper level maths, being able to approximate things to a specific error is really important. To know without a shadow of a doubt that our value is going to be between these two numbers, period. I mean, there's no, oh, well, maybe it's 6 point, or 7. Maybe it's 7. No, it is between here. He did enough research to, who knows how long it took him to prove and validate that. He did enough to know that that is true. That's where the error will lie, between those with this bound. So our very first Lagrange error problem. Yay! I know. Okay. So that was actually modeled after an AP question that was on the test several years ago. And so is this next one. And on this next one, they really don't help us out much at all. Notice how on that problem we just did, we had all the derivative values. We got to write the polynomial pretty quickly. They're not giving us any derivative values or anything about the next derivative. All right, so let's tackle this one. Now, sine of 5x plus pi over 3. We want to consider whether we can use the series that we've memorized. Okay, they are centered about the same location, about 0. But do the function values, the derivative values, match up? No. So this one is going to have to be done from scratch. We can't use one of our, nice techniques that we learned to be able to write it. We're going to have to do it from scratch. We're going to have to find the derivatives and the derivative values. So for time's sake, I'm going to write the derivatives and the derivative values over here just so you can copy them down on your paper. I'm not going to go through and explain how each one was found. I'm pretty sure we're okay and know how to do that. But I do want you to have the information. So I'm going to spend just a minute or so writing all the derivatives and the derivative values down for you. So the function is sine of 5x plus pi over 3, and f of 0 is root 3 over 2. And you can double check, sub that in for yourself. Now I'm just going to list all the derivatives and the derivative values at 0. And now how far do we need to go? Yeah, we need to go to 3. So let's list those. Okay, there are our derivatives and our derivative values that we're going to use to create our Taylor polynomial. So let's use that and create our Taylor polynomial. Oh yeah, I sure did. Yep, I have it over here. You're right. I missed it over here. There we go. Okay, now there's not a need to simplify your Taylor polynomial. There really isn't. You can leave it like that. Notice how I just put the derivative value here times, we're centered at 0, so it's a bit easier. And there's our polynomial. Okay, so we got that done. Part A, find P of x. So now they're asking us to use Lagrange error bound to show that f of 1/15 minus p of 1/15 is less than 1 over 1200. Okay, let's pull this apart and see what in the world they're asking. What does this stand for? The real function value at 1/15. Now, I had this question earlier, and I'm going to talk about it right now. Did I have the series up here, or the function? Did I know what the function was? No. I won't always know what the function is. Okay? Yes, I could stick this in a calculator and it would give me this value, but that's not the purpose of this exercise. It's basically, yes, we have the function and we could calculate the exact error that we had. Well, not exact. But what we're doing is we are operating within this, we're learning about that bound, and we're operating within that bound. Okay, so that's what we're working on. So the function value, f of 1/15 minus, and what is that p of 1/15 stand for? Yep, that's our approximation with the Taylor polynomial, isn't it? This one right here. And what does this whole thing stand for? The error. Very good, the error. Okay, basics, all right? We've got to prove that the error is less than 1 over 1200. All right, what resources do we have at our disposal to work on area for this particular problem? Lagrange error bound. It actually told us, right? It's the series doesn't alternate. It'd be nice if it was alternates, but it doesn't. We could use that one, but it doesn't. We have to use Lagrange error bound, and plus they asked us to. So we need to set up our error bound. Okay. We have no idea about a z value, but let's kind of piece this together. So where did we stop? Where did our polynomial stop? At the 3rd degree. So our error is going to be based around that 4th one, the 4th degree. That's what our error is going to be based around. So let's, I have the formula right here. Let's start our formula. Now, I need to erase those derivatives. I hope we're all okay with that and got that copied down just for space to work with the error. So let's look and see what we have. We substituted in. We know we're centered at 0, so there's the 0. We agreed that it needs to be the fourth. So there's the fourth, and look, it's the fourth derivative value at z, at some mysterious z. Where is z located between? And we've got to mention this. Where is z? Between 0 and 1/15. That's where z exists. So when we start going into justification, we have to say that this is between 0 and 1/15. All right, so they want us to, we got that other stuff down, but we need to know about a maximum fourth derivative value on that interval. They did not give that to us. So we have to investigate it. And no, you can't go on your calculator and type in the fourth derivative and allow your calculator to do a max finder to get the maximum value. That's not okay. I know. They don't allow use of a max finder. We have to do it in basically in proof form, in mathematical proof form, not in a calculator button punching form. So just throwing that out there. So what do we know? Well, first of all, we've got to find the fourth derivative. We need to find it. Okay, we've already found all, the first three. Let's just find the fourth derivative. So we go over, we're going to do some investigating. I'm going to write that over here. Basically we're going to do some work over here on the derivative. So our fourth derivative is f4 of x is 625 sine of 5x plus pi over 3. Okay, kind of think back to the squeeze theorem when we did that quite some time ago. When we were wanting to bind sine in, to squeeze sine in, what did we bind it with? Yeah, but isn't sine's maximum value 1 and minimum value -1? I'm just talking about sine of x, right? Or sine of any angle. It's going to be between -1 and 1. So that's how we would start this process. We're going to bind sine, just the sine part, between -1 and 1. Okay, I'm not going to deal with the 625 yet. So the sine of an angle, whatever angle it is between, and it could equal, right? It can equal -1 and 1. So we know that to be a fact. We're trying to investigate a maximum derivative value, so we're messing with the derivative. Now, what if I use this scenario and we make this 625 sine? What would I need to make this? -625. And what would I need to make this? 625. So -625 less than or equal to 625 sine of 5x plus pi over 3 less than or equal to 625. According to this, what is our maximum derivative value ever? Always. 625. Is that going to apply between 0 and 1/15? Yeah, that's our maximum derivative value all the time. We don't have to, since that is the maximum derivative value for these periodic functions that, go back and forth and back and forth, we're good with finding just the overall maximum. We don't have to get in between 0 and 1/15 and try to figure out what that maximum value is. So that is going to be our bound, 625. It's going to be our error, that's going to be this, our derivative, our maximum derivative value. Our maximum fourth derivative value is going to be 625. Okay, so let's rewrite. Okay. Do I need absolute value bars around that? My error, that's my error that I just substituted everything in. Do I need absolute values around this anymore? No, those are all positive numbers, aren't they? Our maximum derivative value is actually a positive number, so we already knew that these things were going to be positive. And how did I get the 1/15th? Where'd that come from? Isn't that the x value that we're estimating at? Yeah, that's what we're calculating the error for, is 1/15th. I wrote this like they wrote that, because they wrote it like that. We're answering the question that they asked us. Now, the last thing that we need to do is show that this value, this bound, is less than 1 over 1200. That was this right here. Okay? So if I put this in my calculator, I can get a value. You could work it by hand. You probably don't want to, but you could work it by hand. 625 is the same thing as 5 to the 4th. I mean, you could work it that way. Let's just kind of cut to the chase, and that is going to reduce to 1 over 81 times 24. And again, that is just because it was done by hand. You would have a calculator, so you would be able to do a decimal approximation. So that value, which is less than 1 over 1200. So this is that value. All right. Now that's a Lagrange error-bound problem that they don't give you anything. You create it all yourself. Okay?